Ladies and gentlemen, thank you very much for coming along here to SANSA in Hermanus, Space Science SANSA. As Mike has kindly said, I'm Craig Rodger from the University of Otago, which is primarily based in Dunedin, New Zealand, down at the bottom part of the South Island of New Zealand. A beautiful part of the country. We have mountains, we have water, we have seals and penguins. So it's a bit like here, except a lot cooler. And I noticed that I've got a reasonable sunburn just from walking around yesterday. It was such a beautiful day here yesterday. Anyway, here's an opportunity for me to talk to you a little bit about some of the research that is occurring across the world involving many people, including my group and some of the people here in South Africa as well. So, I want to start off by taking you back in time to 1957, 1958, when around the world they launched a program called the International Geophysical Year. And scientists all around the world agreed that they would study how the Earth worked, whether it was the oceans, the atmosphere, or space. And this was the first attempt by mankind to try and get outside of the Earth's atmosphere and put spacecraft into orbit. Now, of course, this was also a politically charged time. It was right at the height of the Cold War, with the Soviet Union and the United States vying for supremacy in an engineering sense, a political sense, an economic sense, and a scientific sense. And they were both trying to be the first to launch spacecraft into space. And of course, the United States was confident that they were going to win, because they had the technology, they had the missiles, etc. They were ready to go. And it all worked out very badly for them. They built some rockets, they put a spacecraft on the top of it, they lit the touch paper, and it blew up on the pad spectacularly in front of the world's media. And so that was bad, and they were sad, so they did it again. And it happened again. Okay? And then, as a complete shock to everyone, the Soviets launched Sputnik 1. Successfully launched a satellite into orbit. It wasn't very complicated. It was a thing with a radio transmitter that went beep, and not much more than that. But nonetheless, it was there. It went beep, so you could use a radio receiver to pick it up, and if you knew where to look at the right time, you could even see it there. An artificial moon, the first artificial moon. Nowadays we talk about satellites, we talk about spacecraft, but at that stage they talked about artificial moon. And in fact, relatively recently, I renovated my bathroom. This story has a point, okay? I renovated my bathroom, and in the walls of my bathroom, as we ripped everything out, we found stacks and stacks and stacks of Australian newspapers. I have no idea why in New Zealand there were stacks and stacks and stacks of Australian newspapers stuffed in the walls, but there were. And I went through them, and I found a newspaper from the date of the first satellite launch. Okay, so that was really interesting, and I've got it framed on my office wall now. Okay, so very tense times. The US has failed to launch satellites into orbit. They put a crash program in of new people to try and deal with it. And they launch, in 1958, Explorer 1, the first US satellite into orbit. And it carries a scientific experiment, a very, very simple scientific experiment. Simple just because you want to make sure it's going to work, okay? Because you've gone to the trouble of launching something out there. They flew a Geiger counter into orbit. Now, Geiger counter is a device that measures radiation. And there was good scientific reasons for doing this. If you measure radiation at the surface of the Earth, you get some radiation which is coming out of the Earth from the decay of uranium and the fact that the Earth is hot inside. But as you go higher up into space, you start get to at higher altitudes, you get more and more counts in your Geiger counter. These are called cosmic rays. We know that they're coming from deep space in some process that is still mysterious today. So even in the 20s and the 30s, putting Geiger counters on balloons and flying them up to high altitudes was interesting. You got information out of that. And then the University of Iowa started to work on something they called the rockoon. So they flew a balloon with a rocket hanging underneath it. They popped the balloon and then fired the rocket, and they could get a little bit higher. And that was worth doing. So when it was proposed that the United States of America would launch the first satellite into orbit, flying a Geiger counter seemed like a good idea, because surely that would get you closer to these astronomical sources of radiation. And that's not what happened. As is often the case in science, when you finally pick up the rock and look underneath it, you've always known what you thought was under the rock. But until you actually pick it up and look and find out what's actually under the rock, you're just making it up. And generally, when you look under the rock, you discover things that you didn't know were there. So they flew a Geiger counter into space, and they found that, in the words of Carl McElwain, space is radioactive. They discovered that there was hot, charged particles, electrons and protons, trapped in the Earth's magnetic field. And these have become known as the Van Allen radiation belts. So this is the happy day when the US launched its first satellite into orbit, made the front page of this Australian newspaper, US launches moon, which in a modern context just sounds weird. Okay, and you have, this is a 1-to-1 scale model of the satellite that they launched. You know, it wasn't very big. It's called Explorer 1, and it's being held aloft by Wernher von Braun, who built the rocket that actually worked, rather than the ones that blew up on the ground. James Van Allen, who designed the scientific experiment that went in the nose and found the radiation belts. And Bill Pickering, who was the head of the Jet Propulsion Lab that was putting all of this crash program together to make it work. And they discovered as they flew the sensor around in the space around the Earth that there were these hot particles trapped in the Earth's radiation belts. And I really love this picture of the press conference with Wernher von Braun, James Van Allen, and Bill Pickering there, because it really demonstrates that right at the dawn of the space age, the discovery of the radiation belts, this was a very international effort. Wernher von Braun is historically well known as a German. James Van Allen was from the University of Iowa. He was from the United States. And would you believe it, Bill Pickering is actually a Kiwi. Right? Actually, yes, he was born in New Zealand, went to the same primary school as Ernest Rutherford, quite a lot of decades afterwards, obviously, and then got a scholarship from the University of Canterbury in Christchurch to go to Caltech in California, where he ended up working for JPL. And he ended up being the head of JPL for about 25 or 30 years, right through some of the most interesting and exciting parts of the space race. So obviously I like this picture. Okay, so since then, we've learnt a lot, as you'd expect. A lot of science has gone down the road. We understand much more about the structure of the Earth, the magnetic field around the Earth, the radiation belts. There's an inner belt, there's an outer belt, there's a slot region. There's a lot happening in there. The thing that's actually surprising is that there's still a lot of fundamental unanswered questions in the scientific area, even though the Van Allen radiation belts were discovered in 1958. And if you came along to the talk last week here at SANSA, when Dan Baker from the United States came along to talk about a dedicated NASA mission that is currently flying to discover more about the radiation belts, you would have learnt about a lot of those questions that they're focused on. And I think the last estimate that I read, that is a few years old, that current NASA mission, which is called the Van Allen probes, named after James Van Allen, they've spent about $700 million US on this effort. So, you know, big bickies. Okay, so here's what the three-dimensional structure of it looks like. You've got the Earth and it's surrounded by this donut, which is really the Earth's magnetic field. And inside the Earth's magnetic field, these hot charged particles are in here. And they're bouncing back and forth inside the magnetic field. And I'll talk more about that soon. The issue, though, is not that there are these lozenges in space. It's easy to draw a cartoon and say they're around this location. It's trying to give you the impression of how much the radiation belts change with time. Their locations change a bit, but what is much more important is that the intensity changes a lot. During quiet times, they're very, very weak and very, very small. And during disturbed times, they're big and huge and lots of flux. And the thing that we're struggling to try and understand is how these changes occur and why they happen so fast. In hours, the radiation belts get pumped up from small to big. Factors of 10, 100, 1,000, in an extreme case, 10,000 times more electrons in the radiation belt appearing in the course of a few hours. And this is one of the things that in radiation belt science has always been regarded as being one of the big puzzles. Except that as the measurements have got higher and higher quality over the last 10, 15 years, we keep saying, oh, everything happens so fast, except the timescale gets smaller. If you went away and talked to a scientist 10 years ago, he would say, oh yes, things change in the radiation belt really fast. They happen in a day, maybe just a little bit less. But now we have much better quality measurements, and we say, things are changing on the timescale of an hour, maybe less. We're still trying to work out how these changes can be so fast. Now, where is the source of the dynamism? Basically, everything flows from the sun. And you can have a very cartoon view of the sun, or you can look at the sun in optical wavelengths, and it still doesn't actually look that interesting. It's a reasonably boring sort of image. But the important thing is that the surface of the sun is incredibly hot. Incredibly hot. It's so hot that the material in the atmosphere of the sun is boiling off into space. And it's blowing away from the sun in all directions. This is called the solar wind. So flowing away from the sun out towards the earth and in all other directions, the outer atmosphere of the sun is boiling away. It's a huge amount of material, except the sun is so huge it doesn't matter. It's a tiny amount of loss for the sun. And it's gently going past the earth, gently at a speed of about 400 kilometers a second. Okay? So there's this constant flow of solar wind coming from the earth. But sometimes the sun explodes. There is a boom from the sun, and it throws out a big mass of material out into space. It's called a coronal mass ejection. And if that blast of material from the sun is Earth-directed, it crashes into the Earth's magnetic field and changes what's happening around Earth. And we know that that's an important source of when the radiation belts get really big or really small. It triggers a lot of processes. What we're still trying to understand is, what are those processes? But I can show you an example, a movie of this going on. So you need to work. Yes. Okay, let me just pause it for a moment. So this is from a satellite in space at the Lagrange 1 point, staring at the sun. So the sun is very bright. You know this. Okay? So when you're trying to see this cloud of material come from the sun, if you take a picture of the sun, you're stuffed because it's too bright. You'll be overwhelmed. So you put a blocking plate in front of the sun. You put a disk over the top of the sun. And then you have to have an arm in the image that's holding the blocking plate in place. And then, because the sun is really, really bright, you actually put another blocking plate in place. So that's what we're looking at. This inner one actually lets a little bit of light through. It's not completely transparent, opaque, but this one in the center is completely opaque. What we're going to see when I run the movie is you're going to see clouds of material coming off the sun. And what we're particularly looking for is what they call a full halo. And that's the coronal mass ejection that's probably Earth-directed. Imagine it like this. I have a shotgun. Okay? I point it over here and I pull the trigger. Briefly, you should see a cloud of shot spreading off in that direction. Then I go over here and I pull the trigger. You'll see a cloud of shot heading in that direction. Then I point it at you and I pull the trigger. Briefly, you should see a cloud of shot coming at you, getting closer and closer. That's what we see with an Earth-directed CME. We see this coming at us. Okay, nice and gentle, boom, boom. And then the whole movie gets all scattered, broken up, because the satellite's actually, this cloud of coronal mass ejection is crashing into the satellite. Okay, let me play it for you again quickly. Boom. Okay, so that's what triggers the processes that we're interested in. I said to you that the radiation belts change a great deal. What we tend to be focused on is the impact of killer electrons. Now, killer electrons is obviously a PR term. It's not what we write down in papers. But essentially, we're talking about electrons with energies greater than 1 million electron volts. That just means they're very energetic. The thing about killer electrons is that they can go through the walls of satellites and get inside the satellite to where the electronics are. And so you've got these beams of electrons getting inside, zapping the electronics. They might not do anything, but they also might hit a sensitive spot. And that's the problem. Because you've got this expensive satellite which might get hit by an electron and get damaged. And when there's more electrons, the probability of it being damaged is higher. And these satellites are very expensive. So, let me show you where the satellites are relative to the radiation belts. I said there's an inner belt and an outer belt. I have a laser pointer. I should use the laser pointer. Whew. Okay, so a lot of the satellites that we really rely upon are out at geosynchronous orbit. That's where the main weather satellites are, a lot of the communication satellites, the satellite TV satellites, they're all out here. So they're living inside the outer radiation belt where the fluxes change a lot. So they're in danger. We've got medium Earth orbit here. That's actually designed to avoid the radiation belts. The GPS satellites are living more like out here and in a bit as well. So they're moving in and out of the radiation belts, in and out. GPS is very important. But actually, it turns out that GPS satellites are one of the few satellites that don't really care about this stuff. Because when they were first built for the US Air Force, they knew that they were for war fighting first and civilian application second. And so you can let a nuclear bomb off near quite close to them. They don't really care. They're armored. Every other satellite has almost no weight shielding on it. Shielding is heavy. Heavy means you've got to have a bigger rocket, which means you need a much more expensive thing. You'd rather take the shielding off and take the risk. But not if you're the US Air Force. Then you just pile it on. And then finally we have weather satellites, for example, at low Earth orbit, which are skimming along just above the atmosphere, but they will interact with the inner radiation belt. To give you a feeling for how busy space is at the moment, when I looked up a website yesterday, it told me there's roughly 430 operational satellites currently in geostationary orbit. And it costs a couple of $100 million US to put each one of these up, to build it and then to launch it. It's a huge amount of money sitting out there in space. And every now and again, a space weather event will occur and some of these satellites will die. Not large numbers, but at $100 to $200 to $300 million a pop, it's a big issue. So some examples of satellite losses are listed here. And so the insurance premiums for satellites is really big. So here's an example of a classic event that I really like. Galaxy 15. That was an American geostation. It is still actually an American geostation's communication satellite. So it's at about 36,000 kilometers altitude, orbiting the Earth once a day. Launched on the 13th of October 2015 by a European satellite. And I mean, it's very difficult to get exact numbers for what anything costs because it's a commercial secret, but it's about $200, $300 million in this case. In April 2010, the Galaxy 15 satellite turned into a zombie. So what happened? Basically, there was a space weather event and the satellite went out of control. It wouldn't listen to any communications from the ground. It drifted out of control around the Earth, not listening to any communications and interfering with any other satellite that it went past, because it continued to broadcast loudly. So when it got to the location of another communication satellite, it swamped out the signals from that satellite. And they were trying to move satellites out of the way to keep everything working, because there was this thing drifting around the world, talking loudly, getting in the way that they couldn't control. And this lasted about 6 months as it drifted around the world. And then a funny thing happened, because as the satellite drifted out of control, its solar panels were positioned wrongly, and the batteries on board the satellite went down and down and down and down and down, and it ran out of power, and rebooted itself. And it came back fine. It woke up, it unzombified itself and said, hello? At which point they said, oh good, hello, please point the solar panels this way, charge up, would you drive yourself back to where you're meant to be? And it's now working fine. Okay, so this wasn't written off, but nonetheless, we're still interested in what went wrong. Good satellite engineering though and design there that it managed to reboot itself eventually. Okay, so what zombified the satellite? I did a study with Mark Clouvard, my good friend from the UK, sitting in the back of the room, and we looked at data at low Earth orbit, and we found that right at the time that the satellite was zombified, at 9:45 universal time in the morning, there was this big pulse of hot electrons showing up in the space around the Earth. And when we looked carefully at what was happening, Galaxy 15 was just at that location. It was at the wrong place at the wrong time. Now, this particular phenomenon is called a substorm, and it involves a distortion in the Earth's magnetic field. It's a bit like a big rubber band. You take this magnetic field light here, like a big rubber band, and you stretch it back, and then eventually you can't stretch anymore, and the rubber band goes chunk, grabs a big chunk of plasma and fires it down towards the Earth. And Galaxy 15 was sitting there with all of these particles streaming through it, and it didn't enjoy the experience. And when we went away and looked at what this particular event was like, only 0.1%, 1 in 1,000 events are like this. So it was a very rare event, and Galaxy 15 was just sitting there at its peak, and it got turned into a zombie. For 6 months. Wrong place at the wrong time. So we're interested in understanding those big changes, those rapid changes in the flux of electrons in the radiation belts. Why they go up so fast and why they go down so fast. So if you're a physicist or a mathematician, or most scientists really, you would write an equation. So how does the number of electrons change with time? This will be dependent on how many electrons do you have at the start, what's the source of the extra electrons, and what's the losses. This is a very popular field internationally. There are lots and lots of people who like to study acceleration. How do you take low energy electrons and pump them up to turn them into killer electrons? Okay, so that's a very exciting field. That's not my field. Okay, I focus on the loss of electrons. There are all these people getting excited about this, but someone has to deal with this term, and I like dealing with this term. So my students and many of my friends around the world study the loss of the electrons because there's competing processes. There's processes of making them and processes of getting them away. And as Jeff Reeves said in 2003, Jeff was actually here in Humanis last week, that the response to the radiation belts is a delicate and complicated balance between the effects of acceleration and loss. So we do the losses. So how do the losses work? One of the main sources of losses is actually into Earth's atmosphere. And so it's a coupling mechanism where what happens in space couples to the Earth's atmosphere, particularly in the polar regions. And why the polar regions? Because these particles are trapped in the magnetic field, and the magnetic field lines come down in the polar regions. And so that's where we find that these particles will be lost. If you map the radiation belts in space onto the Earth's atmosphere, you find that they map down into this, in between these two rings in the Antarctic and in the Arctic. And so we tend to do a lot of our scientific work there. Now let me briefly tell you about, just quickly describe the physics of the radiation belt. If you remember back to introductory high school physics, a charged particle in a magnetic field will go around in a circle. It's called cyclotron motion. Okay, so you have an electron out in space experiencing the Earth's magnetic field. It's going to go around in a circle. Same rules apply in space as on the Earth. So it actually goes around in a circle about 1,000,000 times a second, which I can't do. Okay, round like this 1,000,000 times a second. Then the electron is bouncing along the field line, like this. Now that I can almost do, because it can do that in about 1 second. 1 Mississippi. Okay, no. Something like that. It's a bit fast. And then it's drifting slowly around the Earth. When I say slowly, a 1 mega electron volt electron will go around the Earth in about 10 minutes. Okay? So you've got these dominant motions. 1,000,000 times a second. Once a second. 10 minutes. And those are those 3 dominant motions. Now what the electron's actually doing, I need more space for this really. It's spinning along the magnetic field doing this. Mirroring. Mirroring. If we're going to lose the electron into the atmosphere, we want to disrupt the mirror height. So where it's going to bounce in space, there is the possibility that when it bounces at a lower altitude that's inside the atmosphere. And if it hits the atmosphere, it's lost. So we ended up describing that by measuring what's called the pitch angle. Lots of graphs and stuff, okay? The pitch angle is just the angle between the velocity of the particle, what is the speed and the direction that it's trying to go in, and the magnetic field line. So a pitch angle of 90 degrees means it just sits in one place and doesn't go anywhere, just goes around in a circle. A pitch angle of 0 degrees, it goes along the magnetic field line. If it goes along the magnetic field line, it's going to hit the Earth's atmosphere, it's going to be lost. In practice, there is a small range of pitch angles such that the electrons will get to the atmosphere and be lost. And that ends up defining what we call the bounce loss cone. Any electron that's in the range of angles that is the bounce loss cone will be lost into the atmosphere. Any electron that is pushed into that range of angles by interactions with waves or other processes will be lost into the atmosphere. And that's what we want to study if we want to study the losses. So, what we would like to do is measure the losses into the atmosphere by measuring all the electrons in the bounce loss cone. That would be nice. Okay, we would like to measure that. Anything that's inside that angular range. Turns out that's really hard to do. It sounds easy, but it's really hard. So here's some examples. If you are making measurements from geostationary orbit, the angle gets really, really, really small. The range of angles you want to measure is really small, and because the range of angles is really small, it's very hard to measure. So you don't bother. So we don't have a lot of measurements from there. So then there's a whole lot of satellites which end up measuring close to the loss cone. Because if you measure down at a low Earth orbit, it turns out this cone is much wider, but it's still hard to measure, so they tend to measure that. Which is not completely useless, but if you want to know what's in here, and they're telling you what's in there, it's not right, okay? It tells you something, but it's not what you want. And then there is a small number of detectors which gives you something. Now remember, what we want is this. What we tend to get from those detectors is that. At least we're measuring inside the loss cone, but you're always worried that there might be particles in this angular range hitting the atmosphere, which this detector tells you nothing's happening, nothing's happening, nothing's happening. It's all coming down here. It took me years to work out what was going on with these detectors, why they were so strange. Okay, so we cheat. Space physicists want to do research in space. We want to play with satellites. It's cool. But sometimes, if the satellites simply will not measure what you need them to measure, you have to do something else. And if you're from a country where you're not going to get $100, $200 million to make your own satellite measurement to really study exactly what you want, you have to come up with another solution. Ernest Rutherford had this famous quote, "We don't have very much money, so we're going to have to think." So the approach that we ended up using was to say, we are interested in the loss of hot particles coming from space and hitting Earth's atmosphere. Our problem is we are struggling to measure them in space. And then we realized, Well, they're all hitting Earth's atmosphere. Why don't we use the atmosphere to measure the particles that are hitting the atmosphere? It's not rocket science. So we use the atmosphere as a particle detector to monitor these losses. And we find that for the sort of energies that we're interested in, the majority of these particles will deposit their energy between 80 and about 50 kilometers altitude. So the higher the energy of the electron, the deeper it comes in the Earth's atmosphere, the closer to the Earth's surface it gets. And for traditional sort of radiation belt energies, they'll be coming in between 80 and about 50 kilometers altitude. So you can imagine a situation where there's something like Marvin the Martian flying around in space with a ray gun going bzzzt into the atmosphere. And if he turns up the energy on the ray gun, bzzzt, he can get deeper. I actually do imagine things like this. This is how I do my science. Okay? And so we're trying to work out what's happening when these particles come out of space. And then we need a technique to go away and measure that altitude. How do we touch that altitude range between 50 to 80 kilometers? And that's actually really hard. It's too high for balloons. Balloons don't go that high. Way too high for aeroplanes. Even the secret squirrel spy planes do not fly that high, to the best of my knowledge. It's too low for satellites. If you try and fly a satellite at that altitude, it will fall out of space in about a week because it's constantly ploughing through the very thin atmosphere at 80 kilometers. The Australians did it once in the 60s. I don't know how they got away with it, but it was lost within about a week. You can fire a rocket and get it to pass through that region, but you get measurements for seconds to a minute, and it's quite expensive. So what do? We use a form of poor man's radar. We have a transmitter sending out radio waves, and those radio waves are trapped between the ground, or sea, the Earth, and the lower ionosphere. So the charged part of the Earth's atmosphere. Say 85 kilometers at night, 70 kilometers during the day. And these transmitters will bounce radio waves between these regions. And when a whole lot of energy comes from space and changes the electrical properties of the upper atmosphere, the radio waves will end up bouncing differently, and we can have a receiver here on Earth and we can pick it up. It's a poor man's radar, and I call it poor man's radar because we do not pay for this bit. And this bit is very expensive. We pay for this bit. This bit is very cheap, comparatively. So, what am I sort of talking about? It turns out that these big transmitters, they're called VLF transmitters, very low frequency. That's just, scientists like to name things. So we've given a whole lot of different frequency bands names. But it comes down to the wavelengths we're talking about are on the order of 20 kilometers, a 20 kilometer radio wavelength. Now, it turns out Maxwell's equations tell us that if you want to efficiently send out a radio wave, then your antenna needs to be a quarter of the wavelength or bigger. If you have a 20 kilometer wavelength, you therefore want a 5 kilometer high antenna. Anyone know about 5 kilometer high towers? Anywhere? So no, that's too hard. So what you do is you build a big antenna, which is really inefficient. And then you just pour power into it. Waste huge amounts of power. Heat up the ground around it, literally. And you generate these radio waves. Who would do such a crazy thing? The radiation efficiency is about 5%. You put 20 megawatts in and you get 1 megawatt out. Who would do such a crazy thing? The military. Yeah, ESCOM maybe. The military. It turns out that these particular transmitters can penetrate seawater. This particular frequency range can penetrate seawater, 10, 20 meters. You can sit in a submarine just under the water, and home base can talk to you. So imagine you are a nuclear-armed nation with submarines who want to threaten the world. The only way you can do that is being able to reliably tell your guys when to say no and when to say yes. When should they destroy the world? You need some way of being able to tell them. Generally, you want to tell them, be cool, be calm, your team won the baseball. They actually do send a lot of sporting scores, apparently. Okay, so these transmitters are running 24 hours a day, 7 days a week, telling the submarine crews, the world is still here. A war has not started. Just cruise around. I don't even know exactly what they're saying, because they're all encoded in secret. We don't need to know what they're saying. They're powerful radio transmitters paid by somebody else's taxpayers. We can use them as science tools. So here's my favourite one, because it's in my backyard. It's in the northwest Cape of Australia. It belongs to the United States Navy. It's run by some Australian contractors for them. It operates at 19.8 kilohertz. It radiates 1 megawatt. I'm here in Dunedin. That transmitter is there. If we zoom in on it, you start seeing what looks like an alien landing site. Okay, so we have a central tower, 6 towers in a hexagon in the middle ring, and then another outer ring of 6 towers. Now, the central tower is 390 meters high. The inner towers are about 300 meters high. The outer towers about 365 meters high. This is huge. But they should be 5 kilometers high if they were going to work properly. So very high power output. Notice also the scale, that is about 1 kilometer. It's a big thing. But that's okay. So please meet my aardvark. Our network of receivers and transmitters, the transmitters we don't control, our network of receivers around the world, we named aardvark. And we did that because it's a good name. But now that I'm in South Africa, I have to try and, thank you all for being aardvark people. Okay, so what does it stand for? Antarctic, Arctic, Radiation Belt, Dynamic Deposition, VLF, Atmospheric Research Consortia. My friend Mark and I sat in my living room consuming drinks for several hours to get that. It was a lot of effort to generate aardvark. Okay, each one of the red diamonds is one of our receivers around the world. The green dots are the communications transmitters from major naval powers. If you really like your submarines, if you're a nuclear weapons country in particular, you will build these transmitters. Oddly, the Japanese do like their submarines, but we don't believe they have ballistic missile submarines. And oddly, we haven't been able to find one in China yet. Although some people I know at the US Navy keep saying to me, could you go look at that frequency? We think something's happening. So far, I haven't seen any evidence of it. Okay, and here are all of our friends around the world who are involved in working with us with these various receivers. Myself from the University of Otago, Mark Clover from the British Antarctic Survey, the University of Oulu in Finland, the Australians, the University of Alberta in Canada, Lancaster University in the UK, SANSA here in South Africa, Antarctica, New Zealand, Natural Resources Canada, also in Canada, of course, and Eötvös University in Hungary, in Budapest. And sometimes it's nice to be able to look at our map without all the lines. So we're very happy with aardvark. This is our main science tool. Now, what do we do with aardvark data? Well, I could tell you a great deal about what we do with aardvark data, but it's sort of complicated and it goes on and on and on and on and on. So I thought instead I would try and tell you about one of the things that we've been working on recently, which we think is really, really important. One of the main scientific issues and scientific problems affecting humanity today is man-made climate change. And it's a huge issue. And trying to understand what's happening and what's going to happen in the future is an incredibly important scientific issue. Now, in order for us to do this, we need to be able to predict the evolution of the future climate. And in order to do that, we need to know what the natural climate variability is so that we can then impose what humanity is doing to it. And we know that there are a number of natural sources of climate variability. Volcanoes is one, there are seasonal cycles, but there is also some natural climate variability caused by the sun. And we are trying to understand some of those aspects better. Now, I need to emphasize that this is short-term variability. This is not suggesting that the sun causes climate change. The evidence is very strong that it's us. But if we're going to understand the future climate, we need to understand the link to climate from the solar effects. So I'll end by presenting you with this. A lot of this comes back to some work done by Eugene Rozanov, who is in Switzerland, who took precipitation data, these electrons falling out of the sky, and put them into a simple climate model that he had developed. And this particularly was a chemistry climate model. So it looked at how the chemicals in the atmosphere change and how that couples to climate effects. And he put in the electrons coming out of the sky in the polar regions, and he did a run without that effect and with that effect and looked at the difference. And he, unfortunately this is in black and white because it used to cost lots of money to publish in colour. Okay? He went and did what is the change in temperature? And so over here across Russia, so this is a bit messy plot. There's the UK, there's Alaska, so that means all of this must be Canada. There's Greenland, Japan's over there. So here in Russia, he had a 2-degree increase. In here, he had a 0.5 to 1 degree decrease, and he had a reasonably weak effect over the west coast of the United States. So he reported that there were these consistent changes in the patterns of temperature, simply due to the electrons coming out of space and hitting the atmosphere. And that was very interesting, but no one really noticed, frankly. It was a modelling study. Then some years later, Annika Seppälä from the Finnish Meteorological Institute in Finland went away and looked at reanalysis of climate data and looked at times, the difference in times from when you would expect large amounts of electrons going to the atmosphere and small amounts of electrons going to the atmosphere, and found, this is more like measurements, the same sort of pattern. And she also went and looked in the Antarctic and found patterns here. And so ever since Annika found this, and I'm lucky enough that Annika first showed this to Mark and I in my garden in Dunedin, New Zealand, and we said, "You must publish this." She was a young scientist. She needed some encouragement. And yeah, it's great work. It really has done wonders for her career, and I'm lucky enough to be a co-author on this. So what do we think is going on? You have particle precipitation, you have these electrons coming out of the sky. That produces what they call odd nitrogen and odd hydrogen in the upper atmosphere. Now, I'm not a chemist, I'm a physicist. I don't even really understand chemistry. But my mental picture is that NOx, what they call NOx, odd nitrogen, and HOX are like Pac-Men in the atmosphere. And they destroy ozone. They are catalytic destroyers of ozone. So you've got these Pac-Men in the atmosphere eating ozone. And you end up destroying ozone. Now, ozone's an incredibly important gas in the atmosphere because it absorbs the high energy, the short wavelength light from the sun. The reason that we don't get really bad sunburn here on Earth is that the ozone is absorbing most of the energetic light from the sun. And by doing that, it heats the atmosphere up. So if you take some of the ozone away, you get less heating. And if you get less heating, you will have less hot bits of the atmosphere, which means you'll change the wind patterns, which means you'll change all the coupling. And that might link to climate. This happens, this happens, this happens. We think that happens. We suspect that happens. This is an active research area. Let me show you the bits that we are confident about. Oh yeah, so here's some work that Mark and I did with AARDDVARK to measure the electrons coming into the atmosphere by looking at changes in the signals from the signals that we received in our AARDDVARK data, and we worked out what the flux of electrons must be into the atmosphere, and then we put that into a chemistry climate model, and we calculated how much NOx would be produced. Now this is NOx, these are the nasty Pac-Man chemicals. We said, oh look, big red blob, like a 400% change in the amount of NOx. That sounds dramatic. That might kill lots of ozone. And then we said, what is the change in ozone? And the answer was about 2%. And that's not dramatic and nobody cares. But then we realized that we were doing this at a certain time of year when the sun came up, and the sun kills NOx. Makes it go away really fast. We should do a Gedanken experiment, a thought experiment. We should do it during the polar winter, because in the polar winter in the Antarctic and the Arctic, the sun doesn't come up for months. And so the packmen can live for months and do their thing. So we went away and we said, what happens if the same effect happened during the Antarctic winter? And the chemistry in the Antarctic winter is very different. We only got an increase of about 80% because the atmosphere is very different. But it was very long-lived. And then when we looked at what happened to the ozone, we got decreases of about 25%. And that matters. That's lots. So that was exciting. And then our friends at the British Antarctic Survey put an instrument in the Norwegian Troll station looking up into the sky and measured the production of pulses of NOx in the atmosphere during electron precipitation events. And then our friends from the Finnish Meteorological Institute went away and looked at how much of the HOX, which is the other Pac-Man chemical, was being produced in the atmosphere. And they found that they could explain a lot of the variation in the amount of HOX you see in the atmosphere with the electron precipitation. And in fact, they could see production down as deep as 52 kilometers, which requires really energetic electrons. And then, very recently, we finally found signals in the ozone, large decreases in the ozone after these electron precipitation events. And Monica Andersson from the Finnish Meteorological Institute published that in Nature Communications just a couple of years ago. So, we see quite a lot of the chemical effects, and now we're working with climate modelers. Oh, no, sorry, this is another picture I should show you. So if you look in the winter, between a year that had very large amounts of electron precipitation and contrast it with a year that was very, very quiet, you see between 20 and 30% less ozone in the active years in those altitudes. So, that fits our mental model of what we think is happening. What we're now trying to do is to put this stuff into climate models. And that's really hard, it turns out. But we've just recently been able to get some of what they call the solar signal, so changes due to particle precipitation coming in from space, going into the atmosphere, and also changes in the solar output in UV, and we're just getting that into some testing climate models that they're preparing for the next set of IPCC runs. So that's 5 or 6 years down the road, which is frustrating, but you have to start somewhere. Okay? And so we're working on it. And then we'll try and answer this question. Is this stuff important for natural climate variability? I don't know. I can't tell you. I can tell you that the data suggests it probably is, but we need to do a lot more work before we're going to get there. And the only way this works is through large international groupings of scientists working together, because one person is never smart enough, and generally one person doesn't have enough money either. So between all of us working together, we can solve these sorts of problems. And so that allows me to say, why am I here? Well, to attend a conference here in Hermanus with 55 people from 16 countries, hosted at the Versum and Radiation Belt Conference here in SANSA. It's the 7th conference. That one's me. There's Mike. And so we got together to talk about our science, move our plans forward, understand what each other's doing, and of course, see the whales. So, I need to always thank the people who give me money, who are the Marsden Fund in New Zealand, Antarctic in New Zealand, the Ministry of Business, Innovation and Employment of New Zealand, the University of Otago from New Zealand, and slightly bizarrely, the European Union, who a couple of years ago sent 250,000 euros to New Zealand. Thanks, European Union. Thank you very much for listening to me. It's been a great pleasure for me to have the chance to talk to you.
Diaphragm for man.